Earth, the planet we call home and the only known blue world in our solar system, did not always look the way it does today. Around 4.5 to 5 billion years ago, long before oceans, continents, air, or life existed, Earth was nothing more than a vast cloud of dust drifting silently through space. There were no mountains, no rivers, no sky, only microscopic dust particles and gases scattered across a cold, dark region of the universe. This enormous cloud, known scientifically as a nebula, contained the raw materials that would one day give birth to the Sun, Earth, and every other object in our solar system. The journey from this formless dust cloud to a solid, life-supporting planet is one of the most dramatic and violent stories in cosmic history, involving gravity, heat, collisions, nuclear reactions, and timescales so vast that they challenge human imagination. Scientists believe that the nebula from which Earth formed was created from material expelled by earlier generations of stars. When massive stars reach the end of their lives, they explode in supernova, scattering heavy elements such as iron, silicon, carbon, and oxygen across space. Over billions of years, these materials accumulate in certain regions, forming dense clouds of gas and dust. As more matter gathers, gravity becomes stronger, pulling the particles closer together. Slowly, almost imperceptibly, the nebula begins to collapse inward under its own weight. As it collapses, it naturally takes on a roughly spherical shape because gravity pulls equally from all directions toward the center. At some point during this collapse, a nearby massive star exploded as a supernova. The shock wave from this explosion slammed into the nebula, compressing it further and, most importantly, giving it angular momentum, a rotational motion. This single event changed everything. The collapsing cloud began to spin, and as it spun faster, it flattened into a rotating disk rather than continuing to collapse into a perfect sphere. This rotating structure is known as a protoplanetary disk. At its center, gravity pulled material inward at an increasing rate, while the outer regions continued orbiting around the center. As the disk rotated, matter was not evenly distributed. Tiny differences in density caused some regions to attract more material than others. Wherever slightly more mass accumulated, gravity increased, pulling in even more dust and gas. This runaway process caused clumps of matter to grow larger and larger. Meanwhile, as the disk shrank in size, its rotation speed increased due to the conservation of angular momentum, the same principle that causes a spinning figure skater to rotate faster when pulling in their arms. The faster rotation generated additional heat through friction and collisions between particles. At the very center of the disk, pressure and temperature rose to extreme levels. Hydrogen atoms were squeezed so tightly together that they began to fuse into helium, releasing vast amounts of energy in the process. This marked the birth of the Sun. At first, it existed as a protostar, an extremely hot, unstable young star surrounded by a swirling disk of leftover material. The Sun's intense radiation and solar winds began shaping the environment around it, determining what types of planets could form at different distances. Close to the Sun, temperatures were incredibly high. Only materials with very high melting points, such as metals and silicate minerals, could survive without vaporizing. These materials collided, stuck together, and gradually grew into rocky bodies called planetesimals. Over millions of years, these planetesimals continued colliding and merging, forming the inner rocky planets: Mercury, Venus, Earth, and Mars. Farther from the Sun, where temperatures were lower, lighter elements and volatile compounds like hydrogen, helium, methane, and ammonia could exist in solid or gaseous form. These materials formed the gas giants and ice giants of the outer solar system. Earth's early form, often called proto-Earth, was vastly different from the planet we know today. It was smaller, possibly only a quarter of its current mass, and its surface was entirely molten. There were no oceans, no solid crust, and no atmosphere. Earth was essentially a glowing sphere of magma, constantly bombarded by asteroids and debris left over from the planet-forming process. Each collision released enormous amounts of energy, further heating the planet and preventing it from cooling. One of the most important events in Earth's history occurred during this chaotic period. A massive object, often referred to as Theia, collided with the young Earth. Theia is believed to have been about 4 times the size of Mars. The impact was so violent that it partially melted both bodies and ejected an enormous amount of debris into space. Much of Theia merged with Earth, increasing Earth's mass and gravity, while the remaining debris formed a ring around the planet. Over time, this debris clumped together and formed the Moon. This event is known as the giant impact hypothesis, and it explains many unique features of the Earth-Moon system, including their similar chemical compositions. After this collision, Earth entered a period known as heavy bombardment. Its increased gravity attracted countless asteroids and meteoroids, which rained down on the surface for millions of years. With no atmosphere to burn them up, these objects struck directly, releasing immense heat. The planet was repeatedly melted from top to bottom. During this molten phase, gravity caused heavy elements like iron and nickel to sink toward the center, while lighter materials rose toward the surface. This process, called planetary differentiation, created Earth's internal structure: a dense inner core, a molten outer core, a thick mantle, and a thin outer crust. As Earth slowly began to cool, gases trapped within its interior were released through volcanic activity. These gases formed the planet's first atmosphere. However, this early atmosphere was extremely hostile. It contained toxic gases such as carbon dioxide, methane, ammonia, and sulfur compounds, with little to no free oxygen. The surface remained hot and unstable, with constant volcanic eruptions and lightning storms. Life, as we know it, could not yet survive under these conditions. Water, one of the most critical ingredients for life, began to appear during this time. Some water likely came from chemical reactions within Earth's mantle, while additional water was delivered by icy asteroids and comets striking the planet. Initially, the intense heat kept water in the form of vapor. But as Earth continued to cool, the vapor condensed, falling as rain over millions of years. These relentless rains filled low-lying regions, forming the first oceans. Within these early oceans, the first simple life forms emerged. These were microscopic, single-celled organisms, bacteria-like entities capable of surviving in extreme conditions. Some of these organisms developed the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. At first, this oxygen reacted with dissolved iron in the oceans, preventing it from accumulating in the atmosphere. Eventually, however, the iron became saturated and oxygen began to build up in the air. This increase in atmospheric oxygen dramatically transformed Earth. While oxygen was toxic to many early organisms, it allowed new, more complex life forms to evolve. Over time, oxygen combined to form ozone, creating a protective layer in the upper atmosphere that shielded the surface from harmful ultraviolet radiation. This protection made it possible for life to move from the oceans onto land. Over hundreds of millions of years, life diversified from simple single-celled organisms into complex multicellular plants and animals. Continents shifted due to plate tectonics, climates changed, and ecosystems evolved. Earth gradually became the blue and green planet we recognize today, a world covered in oceans, forests, deserts, and ice caps, teeming with life in countless forms. What makes Earth's story particularly striking is the sheer amount of time it took to reach this point. Nearly 4 billion years passed between Earth's formation and the rise of complex life. And yet, in an incredibly short span of geological time, human activity has begun altering the planet at an unprecedented rate. Earth's long and violent journey from dust cloud to living world serves as a reminder of how rare, fragile, and precious this planet truly is. From a silent nebula drifting through space to a dynamic world capable of supporting life, Earth's formation is not just a scientific story, it is a cosmic biography written in fire, gravity, and time.